right. Hello, everyone, and welcome for this session of SpEC. We are starting with the data track with a guest today. Wanuk is going to share about his insight on working with Apache Nemo with his talk, building distributed system for batch and streaming. As usual, we're doing the questions at the end, and you have a Slido in the invitation. So please, welcome, Wanuk.
Thank you very much. Hello. Hi. Thank you for inviting me to this event. I'm Wanuk Song. I'm a PhD candidate at Seoul National University in Korea, right on the verge of graduating. And today, I'll be talking about building an efficient distributed system for batch and stream processing based on my experiences of building Apache Nemo, a data processing framework designed for flexible optimizations on runtime components. All right. So today, as we know, global services like Spotify, for example, are generating more and more data. And it's an important problem to efficiently process them and extract valuable information from these data. As many of you probably already know, data processing can be divided into two big categories, depending on the data that you're trying to target your data processing job. Batch processing targets past data, which is finite and deterministic, whereas stream processing targets incoming real-time data that is conceptually infinite and also can be out of order. Depending on the different types of data processing applications, things that are more important might be different for each of the jobs. However, commonly they target fast execution, high throughput, fault tolerance, and accuracy. But batch jobs, they focus more on the incremental progress without stragglers. And stream jobs focus more on timely results for fast outputs. While optimizing for these requirements, it is crucial to understand what is happening with the underlying runtime with a given resource environment, as many problems often emerge depending on the resources that you're running your data processing applications on. For example, you might want to process data that are scattered around the globe. In this case, the heterogeneous network connections cause the workload to function unevenly and unpredictably, causing stragglers. You could accumulate all data to a single data center before processing for jobs like repetitive batch jobs. But if you're trying to run a real-time stream application on these jobs, you might want to consider the different bandwidths before scheduling these kind of jobs so that they run more efficiently. Next, you might also want to utilize transient resources like spot instances to cut down on your budget. But this causes container evictions, which lead to data loss in your workloads. It's difficult to maintain progress in such cases. For these examples, scheduling your tasks on the right nodes is an important problem to solve. Moreover, during the execution, we could be facing problems related to the shuffle operations between different executors, which are crucial in distributed data processing in order to accumulate those valuable results from distributed partitions of scattered data. One main problem in batch workloads is a large on-disk shuffle problem that occur immense disk read overheads from its source tasks, and moreover, all data analytic jobs can suffer from data skew, which causes a particular reduced task to be loaded with a particularly large amount of data due to a small number of highly popular keys. In this talk, I'll first describe how batch and stream workloads execute in data processing systems and point out the runtime components that we can optimize to deal with these problems. First, let's look at an example word count application. It's going to read lines, split them into words, filter the empty ones, group them together by words, and finally write results. These applications can be conceptually represented by these directed acyclic graphs consisting of multiple computations. These computations are connected with edges that determine the data dependency. A one-to-one data dependency typically is like a map function that takes an element to output a single corresponding result element. And the shuffle data dependency takes its specified data from multiple source partitions to accumulate the result for the designated keys. Due to such reasons, computations with one-to-one dependencies can be grouped into a single stage so that these computations can be pipelined together without incurring communication overheads, while shuffle operations determine the boundaries of these stages. These stages then can be split into a specific number of parallel tasks, which each are allocated with a specific partition of an input data to concurrently process different parts of the large original data. Now, in order to process these data analytic jobs, one has to first set up a cluster and then allocate a number of containers, usually provided by resource managers like Kubernetes, Yarn, or Mesos. Depending on the application, these clusters can be set up under different environments, like geo-distributed clusters, geographically distributed clusters, or cheap spot instances running on SSDs or hard disk drives, and so on. In a typical batch job, a master node is very important because it first has to schedule tasks and track the progress of the job. While the master schedules stages one after another in batch jobs, depending on the environment, the master could schedule specific tasks on specific nodes so that they execute more efficiently. With appropriate scheduling, batch jobs progress stage by stage, one after another, intuitively. The communication between the tasks occur based on data blocks, which are often written on the nodes of the source tasks to be later pulled by the following children tasks as their input data. When retrieving data from the source task, by the way, this part is common with streaming data, reduced tasks of stream jobs as well. They commonly use a hash partitioner that distinguishes the keys that a reduced task has to process. So these reduced tasks are allocated with these hash keys that you have to that are determined by the hash partitioner. So this way, a batch job completes upon executing all stages one after the other. On the other hand, unlike batch jobs, stream jobs have to prepare tasks in advance before injecting any input data. So the scheduling happens all at once for these continuous operators. These continuous operators are injected with source data from frameworks like PubSub or Kafka and pushes the data to the reduced task through data pipes instead of data blocks, which was used in batch. As they process the data within their computations, so the data is pushed to the reduced tasks. Right. Here, as the reduced tasks receive their input data from their source tasks, they keep track of the input data in a mutable local state. So these reduced tasks are stateful, unlike map tasks, which just pass on the elements that they process. Okay. So continuous operators are used by most streaming engines as they provide much lower latency compared to batch or mini-batch approaches. This is like the approach taken by Apache Flink and similar systems. So unlike batch workloads where they determine their progress on the stage of the application DAG, I mentioned that the batch workloads, they progress stage by stage. These stream workloads determine the progress depending on the watermark, which determine up to which time the system has finished processing data. Now, when a node fails in a batch workload, they simply have to re-execute the previous stages to retrieve the lost data. For such reasons, intermediate data can be checkpointed in longer application DAGs in order to minimize the lost progress between the stages. Dynamic optimization in batch also is done in a similar fashion, and they often optimize the latter stages based on the statistics that can be retrieved from the previous stages. Fault tolerance in stream workloads is a little more tricky. They have to see until which point of the watermark the processing has been completed and checkpointed before replaying the input data from that point after recovering from the failure. Dynamic optimization is also tricky with the same concept, and stream workloads require the job to be paused temporarily for the optimization to be done, and requires the system to restart the job from the checkpointed state where it was paused. Due to such reasons, it is crucial for these optimizations, like operator scaling and task migration, to be as quick as possible in stream workloads by using as much async operations, for example, in order to dynamically optimize stream workloads. Looking at how these data processing jobs are carried out in the runtime, we now know that which components of the data processing systems are used. The master first allocates tasks on the executors with its scheduler, where each source task retrieve data from distributed storages or services like PubSub or Kafka, and communicate with each other for shuffle operations, which collect data to reduce them into a particular result. From this, we figured out that most optimizations are associated with scheduling and communication, and we focus on optimizing our scheduler with the communication channels. So in order to express this, Nemo provides a number of optimization passes that enables annotations related to scheduling and communication on the application DAG, which we call an IR, which guarantee correctness, reusability, and composability. These three are the three main pillars of our system design. Let's look at this with an example use case. A Nemo pass can be used to handle the large-scale shuffle problem. In this example, a map-reduced shuffle dependency, we see a map task that had finished its execution has written its large-scale data on disk. The following reduced tasks have to try to find the data with their hash keys from the disks of these source tasks and pull the specified input data. However, if this happens in numerous reduced tasks, this results in an immense amount of disk seed overheads during shuffle operations. In order to solve this problem, we try to push the data to a target operator in the way that it will be read by the destination tasks on the disks of the nodes where the destination tasks are placed on, so that these data can be read sequentially by the destination tasks from the disk. This causes the data to be written in order, so it may be a little slower on the writing side, but allows the data to be read sequentially, resulting in a shorter overall execution time. I'll show the results, experimental results after this. This optimization can be expressed in a few simple lines of code on Nemo optimization passes. First, it detects shuffle edges, and then upon these shuffle edges, they insert these relay vertices that simply receive the input data and pass it on to the next one. And we annotate the edges with appropriate properties so that the data travels in the way described in the previous slides. The data is pushed onto the memory of the relay vertex, which writes its output on disk in the way that it can be sequentially read by the following group by key tasks. Our optimization passes can be reused on multiple different application DAGs and are designed not to alter the application semantics, guaranteeing equivalent final outputs for correctness. A simple optimization like this shows great effectiveness in large-scale jobs exceeding the scale of 1 terabyte. As you can see on the graph, we did an experiment on a cluster of 20 EC2 instances. And here we can see that Nemo outperformed SpEC in both 1 terabyte and 2 terabyte cases as the input data size gets larger. The disk trace also backs up on how such result had been produced. SpEC shows a very slow disk read speed due to the disk seek overheads, while Nemo shows a slightly slower disk read time here compared to SpEC, but a blazing fast disk read time by making the data sequential on disk. Another example I want to show is related to efficient scheduling. When we are trying to run our applications on transient containers like spot instances to save on our budget, we can face container evictions that can lose both our computation and our data. Here, we focus on the fact that communication patterns with data coming from multiple sources, including shuffle, join, collect operations, they incur much more effort in restoring their lost computation. They have many dependencies from the source tasks and cannot be recovered easily compared to the one-to-one and broadcast communication patterns, which usually require data from a single source task. In a map-reduce example, with a shuffle dependency between them, we'll try to place the reduced task with more valuable dependency on reserved tasks, or reserved containers, and map tasks on the transient ones. In conventional data processing systems, these tasks are scheduled without considering the differences on the executors, whereas we try to allocate different operators based on the different types of containers. Let's consider a case where transient containers are evicted due to the instability of spot instances. In this case, we can see that the shuffle data is lost in conventional engines, whereas Nemo keeps the shuffle data intact within the reserved container. Such evictions consequently cause conventional engines to recompute 5 tasks, but in our example, cascadingly, meaning that such cascading recomputation gets much more serious with longer, complex applications. In Nemo, we can see that it prevents recomputations caused by evictions of transient containers by quickly letting them escape to the reserved containers after their computation. Such optimization can also be expressed with these few simple lines of code in Nemo optimization passes. According to the pass, we place operators on transient resources by default. And upon facing shuffle edges, we mark the destination operator to be placed on the reserved containers and try to evacuate the data as soon as possible with the push property. For operators that can be pipelined from operators placed on the reserved containers, we also mark them to be placed on reserved containers to use the data locality and prevent network communication. In this example, we can also see that these annotations are also reusable and do not alter the computational semantics, providing equivalent, correct final outputs in the end. Evaluations on transient containers also show that Nemo provides a much shorter job completion time compared to SpEC, and similar performances with Pado, which is another ad hoc system that implements this idea. What Nemo is special about is that these optimization passes can be combined together in environments where these problems coexist. For example, let's consider a case where we want to use our transient spot instances while performing large shuffle operations on disk. In this case, we can apply the large shuffle pass before applying the transient resource pass, which places these operators in the way designated by the optimization passes, which our system also checks for the conflicts between these policies, these passes, and confirm that they work correctly. Combining these policies together can solve problems further by solving both resource problems simultaneously. This is very difficult to do in ad hoc systems if they had not been initially designed to be composable as in this way. Before I finish, I also want to briefly go over the data skew problem, which might be interesting to many of you guys. Here, the problem exists due to the data that is skewed towards popular hash keys, which is pretty common in the world. So we have, for example, in Spotify, you can have like artists that's super popular. They have the most data towards those keys. So these kind of skewed data has, if reduced tasks are just allocated with a random hash number, this is going to cause the one with that popular hash keys to become straggler tasks, holding the job from finishing. In our optimization, we try to dynamically measure the histogram of these data volumes for the different hash keys and dynamically allocate reduced tasks with appropriate hash keys so that the data can be evenly distributed throughout the workload. Right. So our system is built with about 32,000 lines of code in Java. The project can be compiled from source using Maven, and it bases itself on Apache Reef, which is a framework that makes it easier to build distributed systems with support of resource managers like Apache Hadoop Yarn and Apache Mesos. Apache Nemo is open source, and you can see the source code online on GitHub, while most development had been going on internally for research purposes recently. More details about Nemo can be found on our papers. We have a journal paper and a conference paper. In this talk, we have seen the common and different parts of stream and batch processing, and have pointed out that resource problems are the main causes of problems in data processing. We were able to discover solutions that fix the scheduler and communication channels to adapt to these problems. To share a little bit about our further research that is being done on our system, we are currently working on automatically finding the right number of parallelism for each of the stages for different workloads, as well as efficiently using new types of resources like functional Lambda instances, and also to provide fast dynamic optimization in wide area distributed stream workloads. All right, thank you. That's it for today, and I'll be happy to take your questions.
Do you have any questions? Yes, we have a few questions on the slide. Okay. All right, so I will take a few questions from the Slido. First question. When you talked about like dynamic batch optimization, the idea was to bring statistics from the previous stage to the new stages. Mm-hmm. What are those statistics?
Right. So, for example, right before I finished, I mentioned handling data skew. So, what's difficult about this is that these skewed data is not predictable in the raw data. So, after processing, for example, like a couple of stages in your application, then you can measure these histograms where you can find how much data had been, how the distribution of data is among the hash keys. And that way you can dynamically choose which hash keys to dedicate to each of these reduced tasks. Mm-hmm. Okay. Shall I read out the next? Yeah, okay. Nemo seems to be oriented around optimizations in MapReduce and compared to SpEC. Can you talk about how it compares to what's outlined in Millwheel and Dataflow? So I think the question is asking about stream workloads, right? Also for stream workloads, okay, the question is changing. But anyways, right. But I'm guessing that compared to SpEC, you're meaning that it seems a little batch oriented, but also on stream workloads, you can do these kind of optimizations on the initial scheduling as well as on the communication channels. So all well, like for example, like the transient resources, you can run stream workloads on those spot instances where you can dump your data and process whatever workload. I'm trying to find the example, but if you're running a MapReduce word count on streaming data, you can also place those different tasks on different resources that you want to place your tasks on, depending on their characteristic. Okay. So do you think these optimizations, fault tolerance for transient containers, make it feasible or desirable to use cheap spot instances for important and time-critical jobs? Will this also work for streaming systems? Okay. So for batch systems, I talked about fault tolerance and how to dynamically optimize these batch and streaming jobs. They will work for streaming systems if you have those checkpoint mechanisms stored up, but it will cause the data to be rolled back. So you have to start again from the checkpointed state on those streaming systems, and you will be able to use these transient resources. So this is like a costs and quality kind of trade-off, where if you find that these faults are tolerable, you can use these cheap spot instances for those jobs. Right. If there's any additional questions,
Any other questions?
Mm-hmm.
Okay, so maybe I can go with mine, if we have time. Quite similar to the previous one, I had that question. I may be putting in a different way, but we talked about fault tolerance when it comes to streaming, and I was expecting that since we're talking about streaming, at some point we could maybe cheat a little bit, because there is also the concept of delivery semantic. Let's say that I'm at least once, I can like reproduce some processing, and I accept that, okay, things are continuously going, and I can like repeat operation if I fail, because I'm on delivery semantic that is at least once. I would expect us to be able to like cheat a little bit and not having to track the watermark. Is it something you're considering with Nemo? Are you like also taking into account the messaging system that is sending the stuff and the acknowledgement of the messages?
Sorry, I didn't get the question. It was
my question is, are you always forced to track the watermark when it comes to fault tolerance, or could you just rely on the commit of the messages of your streaming platform?
Are you talking about the input data?
Yes.
So, sorry, I didn't get what exactly it was.
Instead of checking the watermark.
Instead of checking the watermark, okay.
Yes. Could you just at the end see if the message went through the entire pipeline?
Well, the thing is that we're checking the watermark is that we want to keep track of which data had been processed from those that haven't, as well as processing out of order data. So as long as also what the system does is that this is actually a part of Apache Beam, but Apache Beam has this system that enables the system to know the progress of the stream workloads by with watermarks, and also has triggers in the end which also allow for these latecomer data that's out of order. So we do have support for all these operations that Beam supports. So Beam takes care of those messy input data.
All right. Another one for me.
Right.
We've been talking about quite a few benchmarks. Could you just clarify the setup again for me? It is when it comes to Nemo, it's Beam on Nemo compared to Spark.
Yes. So it's Beam on Nemo. Nemo currently supports Apache Beam as its first-class data flow programming semantics. Compared to Spark, it's the same data flow program that's being run on Spark in our experiments. Yes. And by the way, if you're interested, I have these experimental settings that it's for more details.
Oh, great. Then, thank you, Wanuk.
Okay, thank you.